Today we will look at some of the results that is obtained by solving those equations. So, you can based on the equation derived in the last class, you can estimate the reflectivity of a layer of particles depending upon the single scattering albedo, which is the x axis here, and the albedo of the cloud of particles in the y axis. And this result is shown for two different asymmetry parameters. One, it is for isotropic scattering, which we had derived earlier. So, in this case scattering is uniform in all directions, and you find that the reflectivity of the particles increases linearly initially for small values of single scattering albedo, that is when there is a lot of absorption, less scattering, and as scattering increases it approaches a value of 1, which is to be expected. But notice that this x axis is not a linear axis, it is a logarithmic this one. So, the approach of the albedo of the cloud of particles to unity is very slow. You can see that you go from 0.9 to 0.99, the albedo increases from around 0.4 to 0.8, and from there to reach 1 takes a lot more increase in the single scattering albedo. Next, we see the case where there is more forward scattering. So, if there is forward scattering which is more than isotropic, then you must realize that there is less backward scattering. So, albedo is nothing but backward scattering. So, if there is less backward scattering, the albedo of the cloud of particles will be less than for isotropic scattering all the way from 0 value of single scattering albedo all the way to the higher values. But the basic shape of the curve is similar to the isotropic scattering, except that the amount is somewhat reduced because the scattering is not isotropic and more of the photons are being scattered in the forward direction, and hence less photons available for reflection or backward scattering. So, this also gives a rough idea of the kinds of errors one makes when you assume isotropic scattering. You can see clearly from this picture that if the single scattering albedo is quite low or less than 0.9 or even less than 0.99, there is a large difference between the results for isotropic scattering and non-isotropic scattering, indicating thereby that you have to be very careful about the assumption of isotropic scattering. We must be aware that when you assume isotropic scattering, you can overestimate the albedo of the cloud of particles by as much as 400%, if the single scattering albedo is 0.9. But if a single scattering albedo is very, very large, 0.999, very close to 1, then it does not matter what assumption you make about the nature of scattering. So, what this really means is, if the particles are predominantly scattering, then you can assume that the albedo will approach 1 irrespective of the nature of scattering, whether it is isotropic or non-isotropic, because if the single scattering albedo is so large, ultimately the photons will be backscattered after large number of scattering within the medium. Large number of events of scattering will ultimately take it back to leave the slab of particles, and so it does not matter whether the scattering is isotropic or non-isotropic, as long as the single scattering albedo is very large, ultimately it will all be scattered out of the system. By the same condition, let us now look at the effect of the total optical depth of the slab of particles and the transmittance. Now, in the case of transmittance, you see that as the single scattering albedo increases, the transmission is also increasing. Okay. And so, that is understandable, because as the single scattering albedo increases from 0.9 to 1, the absorption is decreasing. If the absorption is decreasing, transmission should increase. Okay. And again, one notices that when the total optical depth is of the order of 10, there is a large impact of the single scattering albedo on the transmittance. You can see that when the single scattering albedo goes from 0.9 to 1, the transmittance can go from 0 to 0.4, very large effect of single scattering albedo. On the other hand, if you are here at very high optical depth, then it does not really matter what the single scattering albedo is. Whatever single scattering albedo, ultimately your transmission is very small, because again, if the optical depth is large, the photon gets many opportunities to be absorbed within the medium. And so, as the optical depth increases, you are going to find that the transmittance is going to go down, irrespective of the value of the single scattering albedo. See, these are very useful lessons one can learn from a simple model, because it gives insight into the behavior of the system. Now, in the next graph here, we see again the connection between albedo, which is backscattering, and the optical depth for various values of single scattering albedo. Again, you will see that if the optical depth is very small, albedo will be very small, irrespective of the albedo of the cloud will be small, irrespective of the value of the single scattering albedo, because the optical depth is very small. But when the optical depth is large, when the photon has many events within the system, then the single scattering albedo matters. You can see that as the optical depth becomes of the order of even 10, going from 0.9 single scattering albedo to 1 increases the cloud albedo by 3 times, 300%. And if the optical depth is of the order of 100, then going from 0.2, the single scattering albedo of 0.9 causes albedo of 0.2, while 1 causes albedo of 0.95. So, again there is a large increase in the cloud albedo in response to change in single scattering albedo when the optical depth is large. Okay. Now, the next quantity is the opposite of 1 minus albedo minus transmission, what is absorbed in the system. And again you see clearly that if the optical depth is small, absorptance is small, does not matter what the single scattering albedo is, while at high optical depth the amount absorbed depends very much on the single scattering albedo. When the albedo is 0.9, the absorptance is 0.8. So, at every scattering encounter, there is only 10% chance of absorption, but since the optical depth is so large, there are many opportunities for the photon to absorb, and ultimately 80% of the photons are absorbed. While if the single scattering albedo is 0.999, then the chance of being absorbed is only 10%. So, again you see a very interesting nonlinear relationship between single scattering albedo and the total photons absorbed by this slab of particles. And here you see the importance of minimum thickness. Very often there are simple results for semi-infinite medium available, and one needs to ask whether the assumption of semi-infinite slab is a valid approximation in a given situation. So, this result here in this graph will help you to decide up to what optical depth can be considered as semi infinite, and that depends upon the difference of single scattering albedo. As single scattering albedo increases, there are more and more scattering events, and so you need a much thicker layer of the medium for you to treat it as semi infinite. And it also depends upon whether you have more forward scattering or you have isotropic scattering. So, with this we conclude the discussion on the use of simple scattering models to estimate the albedo of a cloud of particles as a function of the single scattering albedo and assumption about asymmetry parameter. Now, we move on to another technique in solving the equation for scattering, and this technique is called the discrete ordinates method, also called DO. So, let us assume that you are dealing with a system of particles which are scattering, and the scattering is isotropic. So, this is just to make the analysis simple. This can be extended to non-isotropic scattering also, but the method is best illustrated by isotropic scattering. Now, for radiation which is azimuthally average, azimuth if you recall is the angle which goes this way, this azimuth that you average over. Once you do that, your equation for intensity in the absence of emission reads like this is a phase function, and you can also add direct term representing solar energy radiation coming directly on the medium. This is the diffuse, this is the direct radiation, and this can be written in terms of the incoming radiation as 0 and phase function of mu and minus mu 0 because sun is coming from the top, and e to the power of minus tau by mu 0. So, this is direct radiation which is being scattered by the medium. The rest are all radiation coming in all directions. If you assume that the scattering is isotropic, scattering phase function is 1, you can integrate over all of the mu there, then you can write a much simpler expression in which the mu integration is the p mu prime is 1. So, finally, we have an expression which says the rate of change intensity with optical depth is equal to the value at that tau and mu minus the single scattering albedo, how it varies with mu here, minus omega direct radiation by 4 pi e to the power minus tau by mu 0. So, this simple expression for isotropic scattering, and now we would like to solve this equation for intensity, and in order to do that our main complication is this integral. This integral is what is going to cause a big problem for us, because the unknown function is inside the integral. Okay. So, we adopt the following strategy. We replace this integral -1 to +1 I tau mu prime d mu prime by a simple quadrature. Now, today all of you are computer savvy, and you know that there are many methods available to replace an integral by a summation. So, these are the AJ are the Gaussian weights, and mu j are the various directions, discrete. So, essentially what you are doing is replacing the continuous variation in this integral by discrete directions. So, you have to continuously vary mu from 0 to 1, or sorry, rather -1 to +1. Now, you are going to decide to replace it by maybe 2, 4, 6, 8 or 16 directions, and then for each of the direction you will find an appropriate weighting function. Now, once you substitute this back here, you have a system of, let us do that to make sure we understand what is going on here. Once substitute, they will get the following equation. So, this is the integral I have replaced now by summation. This solar radiance coming at a specific angle mu 0, and so we have now, remember, 2n equations for 2n values of mu. So, that is the we have, and it is a inhomogeneous because of this term. Differential equations. So, there are well known techniques available to solve a set of simultaneous differential equations, linear, everything is linear here, and so many of you have learned how to solve the equations. So, let us say that we assume that in the ith direction the solution is of the kind some g I e to the power minus k times tau. Okay. So, you insert this form of the solution into the equation, and collect all the terms with the same mu direction, then you will get G I into 1 plus mu I k. This mu I will come from here, okay, is equal to omega by 2 sigma j equals minus n to plus n a j g j. This is the homogeneous solution, because we are going to include the second part. This is a homogeneous solution. We are going to take care of the non-homogeneous solution, because the total solution we will say is equal to homogeneous solution plus particular integral. All of you have done this kind of exercise, in which a non-homogeneous differential equation, first you ignore the non-homogeneous part, solve the equation homogeneous part, you get one solution, then add the particular integral, which will ensure that the non-homogeneous term is taken into account. Okay. So, G I, which is the unknown constant in this problem, will be of the form some let us say B I, some B by 1 plus V I into k. So, general solution now you can write down for the ith direction will be sigma over j b j plus 1 plus mu I k j into the e minus k j into tau. So, this is the form of the solution for the homogeneous term. Then you have minus omega albedo into S 0 by 4 pi into h I, another constant, e to the power of minus tau by mu 0. So, still there is a task of finding the b j's and the h i's, okay. And so that depends on the boundary condition, and we will not get into the details of how we get you have a set of equations, two n equations, and the general solution available. Now, these constants are to be determined from the boundary conditions, and so we are going to assume that these boundary conditions can be discovered by the appropriate conditions at the two boundaries. Okay. So, this is an example of a method which is really an extension of the method we developed for two-stream approximation. So, two-stream approximation can also be thought of as a discrete ordinate technique, except that the number of ordinates was 2, up and down. Here we have gone into a more elaborate technique here, and we have done something more elaborate, and the final form of solution we can write down in terms of the particular integral. I may write down a little more carefully particular integral here. I will. So, this is the homogeneous solution, and particular integral actually will be plus omega S 0 and a gamma, which I will define now, by 4 pi 1 plus mu I by mu 0 into e to the power of minus this homogeneous part, and the real task of finding these constants is to be, so gamma is nothing but 1 by 1 minus omega by 2 sigma j equals 1 to n of a j minus 1 minus mu j squared by mu 0 squared. Okay. So, normally in all the different equations, particular integral is obtained in a simplified way, and the task of satisfying the boundary condition is left to the BJs here, the homogeneous terms, and they are so adjusted that the intensities satisfy certain boundary condition at the top, at the bottom, and at all the interfaces. Okay. It is a fairly tedious procedure, but today it can be done fairly easily on a tool like Mathematica or some other technique. So, a lot of algebra is involved, but today this algebra is not as tedious as you might think. So, that was the illustration of the discrete ordinate method, and you must appreciate that there is nothing but a very systematic extension of the two stream approximation, in which you took one stream up and one stream down. Now, this problem can be solved over 4 ordinates, 4 stream, or 8 or 16, and today with the availability of computer and the very attractive prospects in parallel computing, running this code on a parallel computer using large number of ordinates 16, 30, 64 really will not take much time. So, such routine calculation, which were considered very challenging and tedious 50 years ago, and people like astrophysicist Chandrasekhar developed very elegant and complex methods of solving this problem with least effort, that now is not needed, because now you can use the brute force of the computer to solve any tedious calculation without worrying about time or the computational effort at all. That is done routinely. So, that is why discrete ordinate method is now becoming quite popular. There are standard codes available which will solve the full scattering code using the discrete ordinate techniques very easily. So, this is a very popular method today, and there are software available which easily take care of the solution of large number of simultaneous equation using the discrete ordinate method. Now, it is also important to highlight a few other techniques which have been developed in this area, and the technique which is also been quite popular is the simple harmonic method. I am sorry, the spherical harmonics. I am sorry, the spherical harmonics method. So, as the name indicates, we are going to exploit the spherical harmonic functions. So, we again start with the same equation which we had earlier. Which involves the phase function Now, we make some assumption about the nature of the phase function. We are going to assume that this phase function, which depends on mu and mu prime, can be expanded in terms of Legendre polynomials. So, this is based on the experience that although in the case of mixed scattering, we know that the phase function have a very complex dependence on mu and mu prime. In spite of that, we know that we can expand that complex phase function in terms of Legendre polynomials, which is a typical optimal function for these applications. You substitute this here. So, the advantage is this function now uniquely known, and to go further we need to make some assumption about I. So, for I, the intensity, we are going to assume that intensity can be expanded in terms of also Legendre polynomials. And a function which depends only on the optical depth. So, essentially you must understand the two approximations being made here in the spherical harmonics method. The first approximation is the replacement of the complex phase function in terms of Legendre polynomials, and since these polynomials are used for a long time in many fields, one can be confident that if you choose sufficient number of n values in this expansion, you can represent any real complex scattering phase function in terms of these Legendre polynomials. If the Mies scattering function is very complex, then you need more values of n than if it was Rayleigh scattering, for example, which is a very simple expression. In addition to that, in the case of intensity, we are essentially assuming that you can separate the dependence of intensity on angle with that dependence on optical depth. So, this could be considered somewhat like the separation variable technique we adopt in solving differential equations. So, here we are separating the dependence of the intensity on optical depth and the dependence of the intensity on direction. We are assuming that we can represent the dependence of intensity on both optical depth and angle. Both these values can be separated into a product form, one which depends on the optical depth alone multiplied by a dependence on angle alone. So, this is an approximation, but based on the experience in solving differential equation using separation variables, we know that this technique will work. Notice that we use Legendre polynomials on both sides, both for the phase function and for the intensity function. So, when you substitute this back in that equation, you collect powers of like values of mu, because we want the equivalent value for any mu. So, you collect those functions with like values of mu, and you are able to get all the unknown constants Fn here, and this unknown function of the intensity as a function of optical depth. And you can substitute all this there, and you can realize that you will get a function something like m plus 1 psi m plus 1 plus m psi m minus 1 plus 2m plus 1 into 1 minus omega fm into psi of m is equal to 0. This kind of equation we will get for the unknown size. Now, this is now a set of simultaneous equations, which is fairly easy to solve using matrices and so on, standard techniques that is available today on the computer. And so, the only difference between this technique and the discrete ordinate technique is, here you are not using a discrete ordinate technique, you are not dividing the dependence of intensity on angle to discrete values, you are having continuous variation. So, this technique in terms of angular dependence is bound to be more accurate than what we can do in the case of discrete ordinates. Now, some of the phase function that people assume, of course, there is isotropic, you know that P of mu prime is equal to 1. So, that is a simple problem we have dealt with earlier in this class. But if you go for linear isotropy, linear anisotropy, that is, this is depending on mu and mu prime, but in a very simple way. The simplest function one can assume is of this kind. This is called linear anisotropy, very simple function which takes into account the departure of the phase function from isotropy. If this is too simple, you can go for nonlinear anisotropy. Of second order, and that will look like what you already wrote there, the linear one, and the nonlinear one is typically the nonlinear one has square dependence on both mu and mu prime squared. So, this now completes the formulation. So, with assumption of one of these phase functions, simpler form of this, and this assumption for intensity, we can substitute back, match the terms on either side of the same power of mu, and you will get the complete solution equation. Now, you can see that this simple harmonic method is ideally suited for computer use, because it involves inverting a matrix, and so this can be done for in a more and more accurate way, where having more and more values of the value of m. So, you can see that the simple harmonic technique would be superior to DC coordinate, because it does not discretize in the direction mu prime. It allows continuous variation and hence promises to be more accurate with reference to the direction. So, this technique has also been heavily used in the estimation of the role of scattering, especially when the scattering is non-isotropic. So, both the discrete ordinate method and the simple harmonic and spherical harmonics technique have been widely used to solve many problems involving scattering in powders, scattering in clouds, scattering by aerosols. So, wherever you are dealing with complex scattering problems, one of these techniques is routinely used, and today there are ready-made software available for you to be able to calculate the scattering properties of cloud of particles or an insulation which contains many solid particles, or the natural world containing liquid water, ice and aerosols which scatter the radiation from the sun. So, what you should understand from all these cases we have discussed is that with the availability of digital computers, now there are lots of techniques available to solve the problem with various levels of approximation, from 2 stream to 4 stream to 6 stream to 8 streams, or use the full power of spherical harmonics to resolve the direction very accurately. Now, I will also mention another technique which exploits the simplicity of these equations, which is known as the adding doubling method. So, this method essentially starts with a very thin layer whose optical depth is very small, as small as you please. Since the optical depth is small, you can only assume there is only single scattering. While if you have taken a thicker layer, the photon will at least undergo couple of scattering before it comes out. This is what makes the analysis very complicated, the multiple scattering. So, we have derived expressions for reflectivity, transmittivity and absorptivity of layers, there are only single scattering. Now, we would like to know whether you can exploit those techniques of solving for thin layers to actually get solution for fairly thick layers. Now, the adding doubling method essentially says that we start a thin layer, add 2 thin layers, take the property of the doubled layer, and you can go on doubling this as many times as you want. So, all of you know that by the time you double 5 times, you have 32 times the thickness of the layer. So, we start a very thin layer where we are sure that the single scattering approximation is perfectly valid, and go on adding layer by layer and doubling the thickness till you reach the desired level of thickness of a layer. So, this technique is again very elegant, does not involve solution of any differential equation, because solution of a single scattering layer is well established. We got some of those results, and if you recall, we had expressions for reflectivity, absorptivity and transmittivity of a single layer and also two layers, and this methodology just continued till we reach a required layer thickness, whose optical depth can be 30 or 40 or 50, it does not matter. You start with a layer with very low thickness, maybe delta tau of the order of maybe 10 to the power of -5 or even less, to guarantee no multiple scattering, and then go on adding these layers together. Although each layer is optically thin, the combined layer is optically quite thick. So, this typical layer is 10 to the power -8, not even 10 to the power -5. The people prefer to use it as thin as possible, but since you are doubling it each time you add another layer, and it 2 4 5 32, you can see that this can be used to build a total layer of thickness of the order of 1 by doubling it as much as possible. So, on the computer this technique again is very easy and popular, because all it demands is that you understand the basics of a thin layer, which surely at 10 to the power -8 guarantees single scattering, and then go on adding the results of single layer to get double, 4, 8, 16 times thickness, and ultimately reach your desired layer of thickness. So, this is the technique that is also quite popular along with discrete ordinate method and the only method we not covered, which we will cover soon, is the Monte Carlo. So, traditionally the methods that were popular were discrete ordinates and spherical harmonics, but as the computer power increased and one can do large amount of computation at very short time, the entire approach to this subject has changed dramatically. And the present preferred method for solving complex problems in scattering is by Monte Carlo. Monte Carlo method owes its name to the famous gambling dens of Monte Carlo, where people take chance to win something. So, the spirit of Monte Carlo is that you follow the life of every photon . You will say you follow the life of photon first, from its birth to its death, that is when it is absorbed. So, typically the solar radiation arriving on earth may have of the order of 10 to the power 15 photons. So, that is a large number. So, you would not follow every photon in that encounter, because that is even with all the power of computer today and the advantages of parallel computing, you really cannot do a simulation with 10 to the power 15 photon, that would be very tough. Typically people use around 1,000,000 photons or more, depending on the problem complexity. Now, you might wonder how a million photon can be used to represent 10 to the power of 15 photons, which is a billion times larger. Now, the hope is that you have chosen these million photons at random from the larger set of the actual 10 to the power 15 photons. If you have chosen this truly randomly, then it is a high probability that although we are falling only 1 in a billion photon, the chances are that we will get a result which is not very far from the reality. Now, this must be thought through carefully, and as a matter of fact, the major challenges in Monte Carlo is to prove that we have used sufficient number of photons for your simulation, so that the final answer has acceptable accuracy. Now, that is not easy to show, especially in complex problems where other techniques fail, whether you use discrete ordinates or you use spherical Harmonic method or adding and doubling, to show that in a given situation the Monte Carlo method will give you result of a desired accuracy with about a million photons is not easy to show, but lots of new results have come. It shows that the choice of about a million photons or maybe slightly more will give you answers of adequate accuracy, but this has to be actually be shown as a part of the simulation exercise. Now, why is this method getting popular today? It is getting popular because the computer is getting faster. Parallel computing enables you to follow thousands of photons in parallel, because the basic assumption we are making in all the analysis that each photon does not interfere with the life of another photon. So, all photons have independent lives, they do not interact with each other, and if that is the case, then of course, you are at liberty to run these codes in parallel. So, parallel computing has given a huge boost to Monte Carlo, and as the computers get faster and people learn to write more efficient codes for parallel computing, this technique is going to become the favorite technique for radiation heat transfer problems. The reason why Monte Carlo will become more popular is because it can handle the problems of any complexity. For example, suppose we deal with a scattering, absorption, emission problem in which there is strong angular dependence. So, Monte Carlo is good for a non-diffuse, non-isotropic reflection from surfaces, complex dependence on wavelength, and complex geometry. So, all the traditional techniques that we have discussed so far, whether discrete ordinate method or the spherical Harmonic method or adding doubling method, all these techniques will become expensive if the surfaces reflect radiation in a non-diffuse, non-isotropic manner, and the medium has complex dependence on wavelength, and the geometry is very complicated, three-dimensional geometry. The advantage of Monte Carlo is that it does not really worry about the complex geometry or complex wavelength or complex bidirectional reflection functions, because once these are specified, this method will take into account all the complexities, and the rate with which the computer time increases for such simulations may not be that large. So, Monte Carlo is always being looked at as the technique for solving a problem of large complexity without increasing the computational time by a large margin. So, that is the spirit of Monte Carlo, but one can give a general to Monte Carlo, but to discuss a specific thing is a little difficult, and this will be taken up in the next lecture.